Hello everybody, and welcome to an extra lecture segment for 6838. This is just an optional discussion where I thought I would tell you a bit about a research problem that I personally have worked on and really care about in the area of geometry processing, and this is the idea of developing a notion of a volumetric frame field. So recall during our previous lecture that we talked about one extension of tangent vector field processing on surfaces, where essentially rather than just finding one vector per point on a surface, maybe instead we look for multiple vectors per point that are glued together. And this has applications in areas like meshing. So for instance, if I'm putting quad elements on a surface, I don't really care, if I rotate a quad 90 degrees, it's still just a quad. So we need to somehow deal with the fact that there's sort of two directions per point representing the two sides of our quadrilateral element that we're going to place down. Now, that two-dimensional story has been around a long time, and in lecture we covered two different ways to represent tangent frame fields on surfaces, or directional fields more generally, basically using complex number tricks. The problem is that these tricks don't extend beyond two dimensions. These are things that very specifically require identifying the tangent plane to a surface with the complex numbers, which sadly doesn't work when your dimension is bigger than 2, because now you don't just have a real component and an imaginary component. So unfortunately for us, the basic ideas that were really popular in 2 dimensions don't extend too well into 3D. So a problem that we've thought quite a bit about is something called the hexahedral meshing problem, which is basically the idea of taking a volume and filling it with hexahedral elements. That's like what's shown on the screen here. Basically, a hex element is like a deformed cube. And so a very typical procedure for doing that using frame fields is to kind of make a field of 1, 2, 3, 4, 5, 6 directions per point that represent the sort of sides of the cube infinitesimally, and then use that to guide the placement of the discrete elements. Now, broadly speaking, the hex meshing problem is so hard, and there are many open mathematical and topological questions hiding here. So here I'm showing you a very typical hex mesh. Oftentimes we want one of the 6 faces of the boundary cubes to align to the surface normal. And what that ends up doing is implying a certain structure in the interior of this mesh called a singular structure, which is defined as follows. So essentially, if you think of stacking cubes together, and you think about every edge of a cube, every edge is basically adjacent to 4 cubes, right? Left, right, up and down, or whatever. And you see that in this regular cube structure. But in the edges that are highlighted in blue in the interior, if you look really carefully, you'll see that they're adjacent to a number of cubes, which is not just 4. So for example, the one that meets the face closest to us here is actually touching 5 different cubes. So if you extract just those singular edges in a hex mesh, they actually form something called the singular structure, or singular graph of the hex mesh. And already there are actually open mathematical topological problems. For example, if I give you a volume and I give you that blue singular graph, to my knowledge, it's unknown whether there are sort of sufficient or necessary conditions where you can look at that singular graph and quickly verify whether or not there exists a hex mesh of that volume for which that graph is the singular graph. Moreover, the precise relationship between these discrete meshes built up out of big cubes and these infinitesimal fields is a tricky matter. It turns out the space of fields is much bigger than the space of hex meshes. So just to give you a tiny feel for why this stuff is so hard, remember we talked about the Poincare-Hopf theorem in class and what it means to be a singular point, like just counting, things cycling around a vertex. Here I'm showing you all kinds of crazy singular structures that can happen in a hex mesh, each of which corresponds to an equally crazy singular structure in a field. So these are basically just all obtained by stacking deformed cubes together in different topological ways. And there's a whole topological classification of singular vertices and singular edges that people have been exploring in the research community. So here I've given you a pointer to one of our own papers that gives a sort of incomplete exposition of some of the things that we know about the topological structures of these crazy objects. In any event, disregarding that for now, just to focus on the field aspect of this problem, a very typical meshing pipeline looks like the following. So you have some now tetrahedral mesh of the volume that eventually you want to place hex elements in. Your first step is to solve a field design problem. But you don't just want a vector field, you want this object called an octahedral field, which is basically like plus or minus x, y, and z. Like it's plus or minus the 3 side directions of the cube at every single point in the interior of the volume. So here I'm showing you the flow lines of an octahedral field in a volume of a sphere. If you look really closely, you can kind of find some of the singular points and curves. And then based on that, using a technique typically called parametrization, and this goes back to techniques largely by David Bomis and Leif Kobelt, what you might do is map the volume into some other region where now those flow lines of the octahedral field are just like the XYZ axes locally, and then take a grid in that XYZ universe, pull it back, and what you end up with is a hex mesh like on the right-hand side. If you look really closely, you can see that the singularities in the frame field, like the curves around which this field circulates, end up corresponding to singular structures in the hex mesh. Now, I am wildly skipping over many, many really, really non-trivial things here. I encourage you to take a look at papers like Cube Cover and Hex X, which cover the sort of necessary steps that you need to go from the middle picture to the right-hand side. But we're going to focus on going from the left picture to the middle here. And this is basically computing frame fields and volumes. So here are some more examples of some interesting volumetric frame fields, which are actually computed using an algorithm that I proposed a couple years back. Several years back now, with our colleagues Amir Vaxman and David Bomis. So the basic challenge here is how do you represent 3 vectors up to sign and up to order at every point in a volume? And that's a really tricky matter. And it turns out that you can borrow some ideas from representation theory to make this work. And this is a really clever idea that goes back to Huang in 2011. And here's Huang's basic construction. What I'm going to do is construct a polynomial. Polynomials show up a lot in this area. This is a byproduct of representation theory. But specifically, this function x to the 4th plus y to the 4th plus z to the 4th. Now, why is this function so special? If I look at its restriction to the unit sphere, that's like what's shown on the upper left here, what you'll see is that this function is peaked specifically at 6 points, plus or minus the x-axis, plus or minus the y-axis, plus or minus the z-axis. So one thing I can do is think of this function as some representation of the frame field that's associated with the x, y, and z axes. So in general, let's say that I switched from f of x, y, z to thinking of maybe I think a better way to think about it is f of x1, x2, x3, or more generally, just f of x like a vector, right? Then this thing is a 4th degree polynomial, right? It's a 4th degree polynomial. Meaning that, well, it's written in terms of 4th powers of things here. So let's say that I want to think about a rotation of this frame. So rather than thinking about the frame that is peaked at plus or minus x, plus or minus y, plus or minus z, I want a frame that's peaked on some other set of 3 orthogonal axes. Here's a kind of clever trick that I can do. Well, if I have a given rotation matrix R, maybe it's an SO3, in fact O3 is sufficient, I believe, then I could construct a different polynomial g of x, which is equal to f of Rx, or maybe R transpose x. Both of those are fine. I always get the transposes wrong. The basic idea now is that I can think of R as some new set of axes that are like maybe rotated away from the canonical XYZ axes. And I want to encode those 3 axes up to sign and ordering instead. Now, here's the thing. If f is a 4th degree polynomial, then so is g. G is also a 4th degree polynomial. In particular, what does that mean? That means that I can write it, in fact, it's a homogeneous polynomial, meaning that there are like no 3rd order terms, right? So what does that mean? That means that g can be written in some generic form that maybe looks like, you know, some term, you know, x1 to the 4th times some coefficient, you know, a plus x1 squared x2 squared times b plus, I don't know, x1 x2 x3 squared times c, and so on. But there are basically only so many different ways that I can multiply x1, x2, x3, and x4 together and get something that is of total degree 4, right? Like here we have 4, here we have 2 plus 2 is 4, here we have 1 plus 1 plus 2 is 4, and so on. So in general, if I collect the coefficients of these different monomial terms, what I'll get is some mapping from each of these functions here into a set of 9 coefficients, which are the coefficients of these 9 fourth-order terms. So basically, Huang's work here says rather than representing 3 axes, maybe using the columns of a rotation matrix, for example, that's perfectly fine. But if I switch the ordering of the columns or the sign, I want my representation not to change. Instead, kind of similar to that polyvector trick that we covered in class, I'm going to look at this 4th degree homogeneous polynomial in x1, x2, and x3 that's obtained by rotating our canonical xyz polynomial here and extract its coefficients, which basically gives us a mapping into, it turns out, R9. Okay, so that's the basic trick in Huang's work. And then there is some follow-up work from Ray, Sokolov, and Levy, which kind of covers how to add a tangent plane constraint on the outer surface. Let me erase it real quick. All right, so here's a really interesting theoretical challenge, which actually was tackled by your TA, David Palmer. Now, I mentioned that you can take all the rotations of this canonical function up here and embed them into R9 by basically looking at the coefficients of all the possible 4th degree monomials that you get when you rotate f. That's a 9-dimensional universe, but we know that the space of rotations is 3-dimensional, right? It looks like SO3, which is to say that there are a lot of degree 4 polynomials which don't look like rotations of the function up top. I mean, for instance, it could be x to the 4th plus 2 times y to the 4th plus z to the 4th. So specifically, when we study these frame field problems, we don't care about all possible degree 4 homogeneous polynomials. We only care about those that we can get by rotating this canonical function. And those, it turns out, cut out a subset of R9 that's called the octahedral variety. And so that leads us to a more careful characterization. So the basic idea here is that really the object that we care about in these frame fields can be understood as SO3, right, like the space of rotations, quotiented by the octahedral group, which is like the symmetries of a cube. So in other words, if I take my 3 axes and I like rotate them 90 degrees, then I actually still have the same frame. This set turns out not to be a group, unlike in the 2-dimensional case, and we're able to identify it with the complex numbers, but it is an algebraic variety which sits inside of R9 using the construction that we just made. And so in our work, there's actually a really nice sort of representation theory perspective that you can use to work out this embedding really, really carefully. And basically, it just gives you, at the end of the day, rotations of this function which are peaked on these 3 axes up to sine, but with, well, kind of quotienting out that sine issue as well as the labeling of which of the 3 axes is which. Notice that this is a significant step up from the 2-dimensional case, which just constructed that polyvector sort of polynomial thing that we did in class. So this is a very modern thing. In fact, you can take this sort of perspective and even allow it to do 3 orthogonal vectors that all have 3 different lengths but are only known up to sine and ordering by borrowing some additional algebraic constructions in a different part of math, known as the orthogonally decomposable tensors, which are kind of like 4th order tensors, which now have these coefficients lambda I in front of them, which we can again encode up to sine. Now, one thing that our paper doesn't cover is what happens when these 3 vectors are not orthogonal to one another. And I think actually it's still sort of an open question what the best representation is in that particular case. In any event, these sort of Odeco frames, as we call them, or for orthogonally decomposable tensors, allow us to do really cool things. So in this hex meshing application specifically, one of the interesting things that can happen, of course, if I take a slice of a hex mesh, I get something that looks kind of like a quad mesh. So away from singular points, but along singular curves, there's still 2 well-defined axes for the quad, and the only thing that collapses is that third axis parallel to the singular curve. And so by using Odeco frames, I can allow just one axis to go to 0 while still allowing there to be an interesting two-dimensional structure. And in fact, that even has some useful takeaways for the energy density. So when you optimize for Odeco frames, you don't just end up with sort of bad behavior right near the singular points. In any event, in this little short kind of 15-minute segment, I just wanted to introduce you to the challenges that appear when you take some of the ideas that we had in our previous lecture and try to make them work in volumes instead of on surfaces. Basically, I've only defined the problem for you. It's up to you guys to read some of these research papers to get a better idea of how they're solved, basically using machinery from representation theory and algebra. So this is a fabulous example where a problem which somehow doesn't feel that complicated of an extension from something we know how to do in 2D actually becomes way, way harder if we just work with volumes instead of surfaces. I think this is really sort of an emerging research area that people are continuing to study, namely hex meshing and its relationship to frame fields, and that you'll continue to see a lot of research in this space from my group and others in the coming years. So anyway, just a fun sort of pointer into the research to give you a little bit of an intuition about the fun problems that we think about in this area, and I encourage you to talk to either of your TAs who are extremely knowledgeable about this particular space. So with that, I'll see you next time.